So what we've been discussing in class is we started talking about fluids, and what we want to do is apply the same knowledge that we have, the same rules about motion, in particular Newton's laws, to fluids. So to do that, if we have a fluid, which is either an incompressible gas or an incompressible liquid, if that fluid then is contained in some volume right here, which I'm just going to show as an abstract cube, um, then if we apply a force to that fluid, then the force is really only be applied to one surface, and so the force is now going to be distributed over the area of that surface. And so we can now talk not really about forces, but we can discuss the pressure, where the pressure, P, is just the force distributed over that area. So now this pressure, the units on it, we can write down as newtons per meters squared, or we can give it a more concise name and call it the Pascal. So in the SI units, 1 Pascal is 1 Newton applied over an area of 1 meter per second squared. 1 meter squared. Okay, so now what I want to do is I want to take a look at how these pressures are going to be applied to a fluid. So imagine that we have a container that is filled with some fluid, and we're going to look at a particular volume. So we're just going to say, I'm going to write down the volume. I'm going to catch it in this cylindrical shape. And what I'm going to mark down is that the height of this cylindrical shape is D. And then I can look at this fluid and say that there is some force which is pushing on the fluid on the top, F0, and then there's another force due to the fluid pushing on the bottom of it. So I'm only looking at the forces in basically one direction, let's say the Y direction. So in this case, we have the fluid, the amount of fluid on top of my volume, which is pushing down with some weight. And then I have a pressure on the bottom of the, I have a pressure down here at the bottom, which is applying a force also to that volume. And so what we can do is we can apply Newton's laws. So we can look at it and say that this volume we have here has two external forces, one from the bottom, one from the top. So F0 is on the top and F is on the bottom. And the weight of the fluid is pulling down. So there are three forces here. We have the pressure on top, the weight pushing down, and the pressure of the fluid pushing back up onto that volume. So if we apply Newton's laws in the y direction, then the sum of the forces in the y direction is going to be equal to 0. The forces that we have are the force pushing on the bottom, basically the pressure on the bottom of the volume, minus the pressure, the force from the pressure pushing down on the volume, minus the weight of the fluid pulling it downward. So the weight is just the mass times little g, like so. Like I said, we don't want to use forces. We would like to use pressures. We like to see how the force is distributed over the area of this volume. So I can change the force then to the pressure times the area, where in this case the area is the ends of my cylinder minus that pressure on top times the same area. So we're looking at basically a symmetric cylinder minus mg is equal to 0. Okay, so now mass is not a good quantity to use in terms of calculating things with fluids because the mass can be distributed over a different shape. So we're going to replace that with the density. So we said the density was the mass divided by the volume. And in this case, for our cylinder, the volume is the area times the height of the cylinder. So if we go back and look at our cylinder here, our cylinder has a height d and an area a. So the total volume is the area times the height, d. Okay, so then we can rewrite the mass as the density times the area times the height of it. And we can plug that back into our equation. So pressure times the area minus the pressure on top times the area minus the density times the area times the height times the acceleration due to gravity, and all of that is equal to 0. So if you notice that the area is in every single term in this equation, so I can factor it out. And so I can divide both sides by the area. So the area disappears, and what I'm left with is the pressure on the bottom minus the pressure on the top minus the density times the height of the volume times g is equal to 0. And so now I can rewrite this as the pressure on the bottom is equal to the pressure on the top of the volume plus the density times g times the height. And so now I've got this equation I can use to calculate what is going to be the pressure at the bottom of my container of fluid given some depth of the fluid. So if I go back and draw my container, and so there's some fluid in here, so here's the fluid level of the container. So at any height in here, I can calculate what is the pressure inside that fluid. And the pressure depends on what is the pressure on top, pushing down on the fluid, and what is the weight of the fluid, basically what is the density. So there's density here, and the depth. And so if you think about it, this equation makes sense because what it's saying is that there's some pressure on top of the container, of the fluid in the container. And so that's applying a force. But then the deeper you go into the fluid, now you're going to have more and more fluid on top of you. And so you're going to have the weight of the fluid pushing down on you. So the pressure, so if we have a diver that jumps into a pool, then the pressure on that diver depends on how deep they are, d, because you have this volume of fluid resting on top, which is pushing down. And you have the pressure of, let's say, the air on top of the container of the pool pushing down as well. So the deeper you go, the greater the pressure that's going to be applied because you have a lot of mass on top. So it kind of goes with our intuition, or at least what you've heard in the past, that the deeper you go, the further and further down in, say, the ocean that you would travel, you now have more and more liquid on top of you, which is going to crush you if you go so deep that the pressures are going to be so immense that it would then start to crush things like, a metal can, or, even people. So another consequence of this exercise is that now if I was to build a container that had two openings to it, and then I filled it with a liquid, so you pour some liquid into here and start filling up this container, then what's going to happen is eventually you're going to reach an equilibrium where the level on each side, once this thing is filled with the liquid, the level is going to be the same. So you're going to reach the same height, let's say D, of the fluid on both sides. So again, that kind of makes sense now. Why that should happen is because if both sides of the container are open, then both sides of the container have the same pressure of the air on the outside of the container. So there's going to be some pressure P0 pushing down on this side. There's going to be the same pressure P0 pushing down on that side. And what you have now is, if the fluid has the same density, which it should since it's one fluid inside this container, then it's going to have the same weight. So at every depth, D, you get the same pressure. So if we had some depth here, you get the same pressure, P, right here. And so in the end, all the forces are in balance. The pressure on top is the same. The pressure from the fluid at each depth D is the same. And so in the end, you should come up with the same height of the fluid inside that container. Okay. So that means, basically to reiterate, that I can calculate the pressure P from whatever pressure is pushing down plus whatever weight of the fluid, basically the density times G times the depth. And so I can use this equation to my advantage. And so what I'm going to do in the next video is go over an example of how to use it.